of HBr. So we remember from our alkene chapter that we can add HBr across double bond to give us the radical species, to give us the Markovnikov, right? And we know that this goes through an ionic reaction. But at that time, it also showed us the HBr with a radical initiator, right? Usually shown as just OOR. And in this case, it gave us the anti-Markovnikov. So today we'll look at the mechanism of why this occurs. Back in that chapter, you remember that I talked about the fact that what adds first to give the most stable intermediate is what is important. And what we learned on Wednesday and what we learned on Friday was that radical stability and carbocation stability are very similar because they're both electron deficient. And so for this to be opposite, when we look at a radical reaction, we have to change what we're adding. And that's what's occurring here to give us a different selectivity. So let's look at the radical. Remember, they all start with initiation. If I spell initiation correctly. Most of you know why I did not become an English professor. So if we look at ORO, okay, we hit that with heat or light. And usually this is heat, but heat or light, right? All we need is a little bit of energy to get that peroxides or not, and that's what that is, an OO bond or peroxides. Those reactions occur pretty readily. They're not strong bonds. Okay, and then that reacts with HBr. And so this is an example where to get the radical that we want, we're actually going to have a two-step type of initiation process. We have the first step creates the radicals, but the second step creates the radical that we're going to take to propagation. So it's this bromine radical that we're going to use to start our propagation step. And after my story on Friday, me and the kids planted some sunflowers this weekend. So hopefully we'll have big sunflower plants going on. But the idea of planting a sunflower and then that creates more sunflower seeds that you can plant again. So propagation, we start with the bromine radical. We have our double bond here, and let me fix that. So then this, we get a radical addition to the alkene. That gives us this bromine, right, with the radical there. So what we've added first is the bromine, right? So the first thing that adds is the bromine radical. That gives us the most stable radical. So we're not changing the laws of Markovnikov's addition, right? We're getting the more stable species, but what's changed now is the bromine is my first thing to add, giving me the radical. So there in the second step, what I need to do is just add a proton, or not a proton, a hydrogen, right? Proton is positive, but we take HBr. Now we get a radical hydrogen abstraction from the HBr. And that gives my H, right, plus the Br radical. So I continue with my reactive species here, right? So bromine goes in, bromine comes out. That's how propagation works. And then last step, right, is termination. And here, any two radicals that come together is a termination, right? So let's pick a couple. Let's say that the two bromines were too close together. They could be a termination step. So we've seen this reaction before. Now we know how it works. The initiator homolytically cleaves into the two radicals. Then that radical extracts a hydrogen to give me the bromine radical. That bromine radical adds to my double bond to give me the more stable radical, which is going to be the tertiary radical here. The radical abstracts a hydrogen from HBr, the bromine leaves, and I get this species with the bromine radical. The bromine radical is giving the Br2. Okay. Questions about this? Okay. The other section that I want to cover in this chapter is radical polymerization. Radical polymerization, if we take ethylene or ethene, right, but ethylene, and react that with a radical initiator, we can end up with a polymer. And let's see, didn't mean to do, right? So this unit, this is known as a monomer, right? And then this would be a polymer, where N, can be thousands. This particular one, because this is ethene, but common name known as ethylene, this is polyethylene. So think milk jugs, think plastic bags, high density polyethylene. My storm shelter is made out of high R is just any group. Sorry, there's a question in the chat. Any group. So any two radicals come together. Yes, high density. Right, so high density polyethylene. And low density polyethylene is kind of like garbage bag. High density polyethylene actually has some structure. And what the difference between it is the conditions, but also the initiator, how the initiator works to start those. And some of these you can use, peroxides are pretty standard initiators. Let's use a peroxide initiator, and let's change this to just the propyl, this will be polypropylene. And let's look at the radicals. So if we take, well, I'm not using the proper protocol, initiation. Right, so if we take a radical, let's take a peroxide, hit that with light or heat. And again, the R's here, there's lots of different radical initiators. It's the peroxide that's important. The change can change in what's going to happen with the R groups can change what temperature. You have all kinds of different temperatures. You have different things like that. And then this, to get this one started, what we'll do is have the O R react with the double bond. And I'm going to flip this around. Do we have a question? If you wouldn't mind muting your mic while you're eating breakfast, I appreciate it. Thank you. And so we end up with this radical, and then this radical does our propagation. And so we end up with this radical here that reacts with another alkene, and I'm showing them upside down. I don't know why, but that's okay. It works out. Right, and we end up with another radical. right? And then we keep doing that until we end up with and then termination is then, you know, two radicals coming together. And again, the R is just any two radicals. And you could pick any of these. You could have two polymers coming together. You could have a radical picking off another, right? One of the termination steps that can occur, and this one we will show because it does change the difference between low density and high density polyethylene, as well as some of the other radicals, is you can have a radical extraction. So let's say we have an R group, and that could be another polymer. Well, let's make it another polymer. So let's say we have a big long polymer here, and I have a hydrogen. Let's keep the R groups out, right? So I've got this big long polymer here, and I have this hydrogen. The carbon radicals here are pretty high energy, and they can also do a hydrogen abstraction, which will terminate the growing end of this polymer. Right, but what it does is then and this is under branching, what it can do is then it creates over here, now a new radical, right? And this radical will cause a branch. Okay. So in low density polyethylene, I don't know why I'm doing it red. What you have is you have a polymer with lots of branching. Okay. But in high density polyethylene, what you end up is with a polymer with minimal branching. You can have some short branches, some long branches, right? And so the radicals can abstract proton radicals from different species. Okay. And that's the last part I want to talk about briefly here. It's not in your book, but I think it's important to understand. Radicals are considerably high energy, and because they're high energy species in most cases, right, they're low selectivity. And what that means then is that if I have, you know, some species out there and I bring in some radical, that radical could abstract a proton. Right, and then that radical then can go add a lot of things. Now, where can we get radicals? Right, sunlight, as we've seen, sunlight can give us radicals. So on your skin, what happens on your skin? If you've ever known somebody that spent a lot of time in the sun, their skin will get kind of leathery. What happens is that the radicals, the sun will actually cause radicals, usually by taking hydrogen bonding hydrogens and homolytically breaking those. And then that can cause a radical, which can cause cross-linking to occur, and then that cross-linking can actually cause skin to be less nimble because you've now cross-linked it, made it harder, and then that can cause more wrinkles, right? Of course, smoking can do this because in smoking, right, and might as well today say vaping, right, you're creating radicals. And here it's you're burning things up, and then the burning it up process you can cause homolytic. Used to be able to tell a lot of smokers because they would have more wrinkles around their mouth than they would have other places. But it also turns out that oxygen can cause radicals. So just the fact that we are an oxygen-based species and living in oxygen can form radicals. So if you take a hydrogen peroxide in oxygen, what you can end up doing is forming these radical species. And then you potentially can even form superoxides, rare, but you can do them. So that's one of the reasons that when you look at the antioxidants, right? What you usually see in an antioxidant, and I should have gotten a picture of beta carotene, but what you've seen in antioxidants is these big long chains of pi bonds that are all in conjugation. And conjugated pi systems also tend to be colored. So one of the things you can do to protect yourself, right, is to eat antioxidants. What that does is take high energy radicals, such as the oxygen radical that we put up here, right, and turns it into a lower energy radical by putting it in this conjugation, right? So that's what, if you look at the chemical structure of antioxidants, what you're going to see a continuous pi system. And that continuous pi system takes a high energy radical and turns it into a low energy radical. And as a lower energy radical, right, high energy radicals are low selective, but if we can create a low energy species, that low energy species is higher selectivity, meaning it'll do less reactions. And therefore we won't have to worry about it modifying a base pair in our DNA. And if you modify a base pair in your DNA, if it survives, then, you know, that's where we get cancer. So, you know, we used to have suntan lotion. Now you have, you know, that was because you wanted to be even darker. So half of my generation is probably going to have some kind of treatment for skin cancer. But you know, now you want to protect your sin. The alpha UVA and UVB, what those are species like this that can absorb that energy, and if it creates a radical, create a low energy radical. Smoking and vaping, just stop that. And then the oxygens, we can't stop that, right? We need oxygen to live, but by making sure that we eat, you know, nice colored vegetables and things. I know meat is red, but I'm talking purples and oranges and things like those. All the reds, those things have antioxidant materials in them. That's where they get their color. Okay, so radicals and health. My little, you know, stay away from. The other one I should say is alcohol. In high quantities, and it turns out that high quantities is just as bad as too frequent. High quantities, it kicks into a secondary metabolism cycle that creates radicals in the liver. Liver. Can't spell liver. Right? And then if you keep drinking, you're going to go to the third stage, metabolism, which can cause radicals in the brain. Okay, so you want to make sure that you're smoking. What happens when you're smoking and potentially in vaping too is when smoking, you're actually burning materials, and so the radicals may not actually come from the nicotine. It may actually come from the fact that you're creating radicals from just burning things. Now, when you heat things up in vaping, it can also cause homolytic cleavage, because some of those molecules in there, even some of the ones that are used for flavoring compounds, when you heat it up hot enough to do that, you may be creating. So it's the heat and the burning and smoking, and it's the heat and potentially ionization, and sometimes the vaping, that will cause radicals to form, right? So under normal temperatures and without a lot of sunlight, you don't see that, but when you heat things up, that's when it can cause. And of course, as Bruno points out, yeah, inhaling anything other than air is not good for you. But for alcohol, what we want to watch for is high quantities of alcohol change the metabolism cycle. After a certain point, your body can't metabolize all the alcohol you're consuming. It doesn't metabolize the same as other things. So it goes from the primary metabolism cycle to the secondary. That can cause liver damage. If you binge drink even more than that, then you go into the third stage of metabolism, and that can cause radical formation anywhere, including the brain. And then of course that can get damaged. So long-term consumption of alcohol on a routine basis, we're talking, daily, can actually cause your body to change the metabolism cycle so that alcohol becomes a major power source. That can cause health problems, but also just binge drinking, even if it's just every, once a month, you go and you drink way too much. What that's doing is that's impairing your liver. And if you keep drinking, that can cause radicals in the brain. Of course, you keep drinking, it becomes toxic because alcohol is a toxin. So, okay. My public service announcement for the class. Okay, so next let's look at synthesis. So we've already kind of looked at synthesis and retrosynthesis. Now we're going to break it down and look at a couple of things. First, carbon skeleton changes. Remember, I keep bringing this up as important, and that's because it's not easy to do. Right now in synthesis, you really only have two main ways to do this, right? We can take CH3. Let me start over. We can take the acetylide process, right? And we can add carbons. So if we look at addition, if we look at subtracting carbons, right, we can take ozone with an alkene, some type of reductive second step. Right? And we can lose one carbon. And then we can change, the carbon structure, right, by a carbocation rearrangement. And there's several reactions that'll do this. So one thing to think about when we're thinking about synthesis strategies is carbon skeleton changes. The next is functional group transformations. We've seen these, right? And there's kind of two classes here. So if we take an alkene, right, we can turn that into bromide. That's one, right? We can just add HBr here. We could turn a alcohol into an alkene, right? So we've been looking at this, and actually this is most of the reactions you've learned, right, is functional group transformation. But we can also have relocations. These are all one-step processes, but you know, when we look at how do you go from here to this, right? Here I haven't changed the functional group, but I've relocated the functional group, right? And we can do this one by adding in HBr. That can give me this functional group, and then I can react with a relatively small base, right, to eliminate, to give me the Sate-Seth product, and I could go there, right? So the things that we want to be watching for, the approach to these, is we want to be looking for two things. So your approach, when you're thinking about these transformations, is one, is there a carbon skeleton change? Now, the thing about this one is it's easy to see, right? But because it's easy to see, sometimes we forget. And what I mean by that is that, in most cases, like up here, it was pretty obvious that the base structure was the same, right? When my eye scans this this image, and my eye scans this image, I can tell they're pretty close, right? It's almost like your mind doesn't analyze everything. It's almost like compression of movies. So have you ever figured out how do you take all these? I mean, movies used to be like 4 to 6 huge reels, and now we're putting them on a little bitty flash drive. The reason that can happen is that they figured out that your mind doesn't always analyze. So right now my mind is analyzing what's moving, which happens to be my hand, and looking up at the screen to see if anybody is writing something in chat. But the wall behind it, my mind doesn't need to analyze that unless I focus on it. So one of the issues that can happen with carbon skeleton changes is that we miss it, right? We miss it because we scan this and those two things look very similar. So therefore I miss the carbon skeleton. So they're easy to see, and in fact, they're easy to count, but sometimes we'll forget to do them. So always think about that. If we focus it on it, our mind will pick up those things, and you'll be able to count and see what's changed in the carbon skeleton. If not, right, our mind often skips it because in most cases we aren't changing the carbon skeleton, right? It's almost like what has changed in the picture thing, right? You've got to focus on every little item. Here, really all you have to do is count and make sure all the carbons are connected the same way. It's easy to see, but we forget. So make sure that you always start with this. And the reason to start with this one is because it's the hard one. It's actually harder than the transformation. And then the second question, right, is there a change and or location of the functional group? And this is the one we've been focusing on, right, so far, because most cases we're just dealing with one-step synthesis. We're only going to change the functional group. So as you're looking at these are the two big questions. What is happening with the carbon skeleton? No change, cool. If there is a change, then that's what you need to focus on. Second, is there a change and or location functional group? Now, if both of these were no, then it's not really a reaction. You're not doing anything. So you should expect one or both of these or multiple of these to be what you're going to be focusing on. Okay, so let's look at one of those now to see what's going on. Okay. And I'm going to use retrosynthesis arrows for some of these. Okay, so this is a retrosynthesis arrow. So let's take a look at that one. And let's take a look at this one. Okay, let's take a minute, go through those two questions. And then once you've answered those, right, then start thinking about how can I do this transformation? And again, retrosynthesis, this is my target. This is where I want to get to, right? This is my starting material. Okay, let's take a look at the first one. Okay, first question, is there a carbon skeleton change? Again, we can do this pretty quick. This one looks like there's not, but again, it's important to go ahead and count them out. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, right? I've got 3 carbons attached to 1 carbon there. These 2 carbons attached to each other, right? Just analyze it real quick. The reason I'm pointing on that is I don't want you to skip through it too fast. Now, you'll get to the point where you're actually doing this in milliseconds. That's fine. But as you're practicing this, take the time to count, take this time to put your pencil on the structure and make sure that it is the same. Then the next step in it is what's happening with a functional group here. Well, we're going from an alcohol, right? And it's terminal. So we even say that's 1 and 2 there. Over here, we're going to an alkyne. And again, we can say 1 and 2. So it looks like our location-wise that our alcohol and our alkyne are in the same place. I'm not really having to move a whole lot, but I'm going to have to go from an alcohol to alkene. Do we know of any straight ways to go from an alcohol to an alkene? No. So then the question is, right, what can I do with an alcohol? And then the other thing is, how can I make an alkyne? Well, this helps us because we know that really the only way to make an alkyne is with a dihalide, right? We can add an alkyne, that's straightforward, that's a acetylide reaction. But here, to make it, what we need is, you know, an excess of a good strong base, right? And a dihalide. So that helps. So how can we form a dihalide? Well, if dihalide I can form from an alkene, can I turn an alcohol into an alkene? Yes, I can turn an alcohol into an alkene. So therefore, looking at this, right, I can figure out how to make this path, and then I can start thinking about how to do this. So let's look at, moving this forward. So first we have the alcohol. Now for the alcohol, I can brute force this, right? I could turn this into a dehydration. But if I want the alcohol to leave, I either have to form an acid or I can form something like potassium chloride. And then at this point, right now, I want to form the double bond. So I need to form a good leaving group, and then I can do the double bond by adding, the ethoxide. Right, and then we get that, right? And then here we add a bromine. We don't want the halohydrin, so we're going to put it in the methylene chloride. That gives us our dibromide. And then here, right, we'll add the sodium NH2. And we'll add excess of that. And then remember, this is a terminal. So what I'm going to do is have to add water to get my triple bond. Okay. Questions about this synthesis? What would have been a potential problem if I had done the brute force with the acid? I might have got a rearrangement here, maybe not, but this one is a little bit cleaner. I don't have to worry about forcing that. And with the quaternary carbon on there, I'm always a little bit concerned about a carbon-carbon skeleton change. Okay, so analyze your steps and then figure out how to go from one place to the other. So Nick, this one, I'm gonna give you a little bit more time. Go through, analyze it, think about your steps, okay? And then we'll look at the answer. Okay, if we look here, right, we know that we're getting 2 carbons is our starting material. We need to make 5 carbons, so we're going to have to add carbons. The acetylide, that gives us a pretty good hint that the thing that we need to do is add our carbons. Okay, so if we look at our structure, this is an alkyne, right, and we have an alcohol. Okay, can we take an alcohol? Can we go from an alkyne to an alcohol directly? The answer to that is no, but we can get an alcohol from an alkene, right? And we can get an alkene from an alkyne. Okay, so if we look at this synthesis, then we can start with our triple bond. We're going to add the base, right, to form the acetylide, and then we need 3 carbons. So I'm going to add a 3 carbon with a good leaving group. The bromide's fine. That gives us the base carbon structure. So now we have our carbon structure. Then I can reduce this, and I can either use hydrogen with Lindlar's catalyst. Right, that's going to give me my double bond, 5 carbons, and then to get the primary, then I can use BH3 and THF followed by the base and hydrogen peroxide. Okay, questions about this one? All right, and the nice thing about the synthesis steps is it helps you try to recover. And remember, recall is a great way to learn this stuff. If you have a partner, you read the questions to them and they try to recall it, they read the questions to you and you try to recall it. Synthesis steps are a way to kind of think about that and kind of bridge. It's also, if you're a chess player, it's a pretty good technique. So let's do a couple more. Again, in retrosynthesis form. I don't know why I drew that line so long. Let's take a little bit of time to look at this one. Yeah, it is great practice for previous chapters. This will help get you ready for the final exam. I'm setting the timer because if I just wait around, I usually tend to do this faster than I meant to. So that's why the timer is going off, because I used to do that in class. I thought I gave the students 30 seconds to a minute to try these, and I was actually giving them 10. When you're waiting, time moves slower than when you're actually doing the practice problems. Okay, so if we look at this one, right, we have 2 carbons over here. I've got 4 carbons over here, right? We're going from an alkyne, right, to, what would you call this? A OH and a bromide. Well, this is a halohydrin, right? So that's going to help you figure out what you're doing when you have these 2 next to each other, right? That's a halohydrin. And so we're going to need to add 2 carbons, and we're going to be changing from an alkyne to a halohydrin. Well, halohydrins come from alkenes, and alkenes, right? Let me draw my arrow the right way. Right, and I can turn an alkyne into an alkene. And you know, both the carbons are there at the end, so that means we can just add to the end. So let's look at our product here. So we start with the alkyne. We're going to do our acetylide reaction. By the time this chapter is over, you're going to know this really well. We just need to add 2 carbons. Right, so now we have that base structure. Now I'm going to reduce, and just to change it up, I'm going to add sodium and ammonia. Get my alkene, and then my alkene, I'm going to add Br2 in water to get my halohydrin. And remember that in a halohydrin, the OH, the alcohol, adds to the more substituted side. So this is the right regiochemistry for this reaction. We could have also used hydrogen and Lindlar's catalyst here. And it might have been better to do that. Sodium, you know, you got to be careful or catch on fire. Okay, let's try another one. Okay, if you're looking at these and you're getting a little frustrated because you're like, how does he remember all those reactions? The more of these you do, right, the better you're going to be able to recall those reactions. And again, make flashcards for each one of your reactions, and you know, take some time every day to look at them. That's how you're going to do it. My kids have they're learning Latin, and so they have a Latin songs they sing to learn Latin. And so, you know, they'll sing it every day, and that's how they figure out another language. This is similar. You've got a set of reactions. So I'm going to set a timer. Y'all try this one. right? So on this one, let's look and see what we have going on as far as our carbon skeleton. So I have 1, 2, 3, 4. I got 4 carbon skeletons here. I mean, 4 carbons there. But over here, I've got 6 carbons. Right, so I must be adding 2 carbons. I'm going from a alkyl halide, right, to an epoxide. We know that epoxides, right, can come from alkenes, and we know that we can get alkenes. We could get alkenes directly from bromides, but there's a problem there, right, to go directly because I need to add 2 carbons. But we know that if we added, you know, the acetylide, then that could get me here. That gets me the right carbons. And then if we think about that, well, then I can go from the alkyne to the alkene. Right? So this direct removement wouldn't have, doing the transformation wouldn't have gotten me to the right number of carbons. So to get the right number of carbons, I'm going to have to use one of my carbon-carbon structure reactions to do that. So I'm going to add, we already have the alkyl halide, so what I'm going to do is add 2 carbons as the acetylide. That gives me my base carbon structure. Now I have 6 carbons. I'm going to reduce that, again, trying to leave the Lindlers, Lindler's catalyst, or P2. Right, that gets me to this species. And then the epoxide, that's part of the reaction to give us the dihydroxyl, the trans dihydroxyl, or the anti-addition of the dihydroxyl. So we know that because of that step. So we can do the epoxide by just adding the peroxy acid, and there's several peroxy acids I could have chosen there. Okay. All right, and that looks like we're about out of time, so we'll stop there. Okay, we'll continue to do a retrosynthesis, probably one a day through the rest of the chapter, kind of like this, kind of a try this. Look through the chapter. There are some helpful hints, especially if you just look at one and freeze up. But one of the things to think about, right, is these approaches, right? Start asking yourself questions. That gets your brain moving. If you just stare at it and you don't know what to do, go back to the questions, and then the questions will help get you to the process, right? These aren't magic, they're steps. So, you know, I've been doing this for 30 years plus, and I still use the steps. You should use the steps as well. Okay, we will see you on